Hi guys, I'm Patrick. The concept I'm going to explain to you today is numerical integration. Now, I can tell you guys are already like, what? Or asleep, so I'm going to draw your attention with a fascinating, captivating topic studied by millions of scholars worldwide. What is it? Video games, of course. What better way is there to explain numerical integration than with an example? And what better example is there out there than a video game? So the challenge I've solved here, and the challenge I'm going to walk you through solving today, is how to use numerical integration to solve differential equations representing the laws of motion. Well, that's kind of boring. So let's get to the fun part. Here I have a space simulator that I programmed using numerical integration, and in this video I'm going to show you how it works in order to help you understand numerical integration.
Before we get into our specific example, let me just give you a brief summary of what numerical integration is. So if you look up, quote, numerical integration, end quote, you get pages and pages and pages of just calculus jargon, which kind of explains why this is a relatively obscure topic. But actually it's really simple, and it doesn't need any calculus to understand. Now, before I start describing numerical integration, let's give a little bit of background information. So the term differential equations, quote, may sound intimidating. I mean, I'm terrified, and I know what they really are. But it's actually just a very simple concept. A differential equation is an equation in which some variables are expressed as the rate of change of others. So, for example, velocity is the rate of change of position with respect to time. This dp dt symbol is just calculus notation that means the rate of change of position, p, with respect to time, t. So if my velocity is 12 miles an hour, then over the course of 1 hour, your position changes 12 miles. Simple enough, right? Numerical integration is simply solving these equations through numerical means. So let's try this with a simple differential equation. dy dt equals y. What? What's that supposed to mean? So I'll try to put this in simple terms that you've come across before. Position and velocity. In this equation, let's let y represent position in miles and let t represent time in hours. I just explained that velocity is the rate of change of position with respect to time. So we can read this differential equation as velocity is given by position. So if we're 1 mile from the origin, we travel 1 mile an hour. And if we're 2 miles from the origin, we travel 2 miles an hour. This second line of the equation represents the starting position. At time 0, we start 1 mile away from the origin. The solution to this equation is going to be a plot of position versus time. So let's get into a specific solution. Now we can use this table to see how numerical integration works. My differential equation says my starting position is 1 mile. If I'm at 1 mile, the differential equation says my velocity is given by my position, so I travel 1 mile an hour. Now, I'm actually going to assume my velocity stays constant, but it actually doesn't. In reality, velocity is always changing because my position is always changing. But, we're just going to have to make the simplifications so we can actually produce an approximate solution. So if I assume we travel 1 mile an hour for 1 hour, I'll end up at 2 miles after 1 hour. At time 1 hour, because velocity is given by position, I'll travel 2 miles an hour, my position, for another hour, making me end up at 4 miles, and I can repeat this process for as long as I want. So congratulations guys, you just used numerical integration to solve your first differential equation. However, the solution I get is actually an approximation of the exact solution, because the key assumption that we've made is that velocity remains constant over the duration of the amount I advance in time, which is known as the time step. So previously, we chose an hour to be our time step. That's kind of arbitrary. We can choose anything else. Let's say what happens if we choose half an hour. What's the result? So here on this graph, the yellow line represents a time step of 1 hour, which we just did. The blue line here represents a time step of half an hour, and this gray line represents a time step of 0.05 hours. As you can see, the smaller the time step gets, the closer the solution gets to this black line here, which represents the exact solution. So just in general, the statement, smaller time steps tend to yield more accurate results. So why is that, you're probably asking? So the key assumption that we made here is that velocity remains constant over the duration of the time step. In reality, velocity is always changing because position is always changing. So the smaller the time step, the more often I'll update velocity, and the more the velocity will mimic the changing of the real thing. So keep that in mind though, that when you're using smaller time steps, you do get more accurate results, but you tend to be less efficient. So when choosing a time step, you kind of have to balance the two. So, bet I know what you're thinking. You're thinking, Patrick, this is obviously a first-order linear homogeneous constant coefficient ordinary differential equation, and everyone knows an exact or analytical solution exists and can be expressed in the form of ae to the sigma t. And of course, you are exactly right. But for most differential equations, analytical solutions actually don't exist. And for the most problems in the real world, there are no analytical solutions. And for the example we're going to look at next, no analytical solution actually does exist. Our specific example is how to solve differential equations representing the laws of motion using numerical integration. So the laws of motion I'd like to focus on here are Newton's second law, F equals ma, in the law of gravity. So these little arrows over the variables represent the fact that these variables are actually something called vector quantities. So vector quantities have three components, x, y, and z. So this one equation actually represents three separate equations, one for x, one for y, and one for z. And this is because the object's actually moving in three-dimensional space. So this vector notation here is just for convenience, so people, namely me, don't have to triplicate each equation and write down the same thing 3 times. Now the differential equations we really want to focus on are the equations for velocity and acceleration. So I've already showed you the equation for velocity. The equation for acceleration is very similar, except velocity is changing instead of position. You've probably seen the laws of motion that I showed you previously before, but your teachers actually lied to you when they taught you. These are actually differential equations. We can write these equations in a form that looks similar to the differential equation we solved before. So this equation here is F equals ma rewritten. It means that acceleration, which is now expressed as dv dt, just like we saw before, is equal to force over mass. Note that when solving this, we actually assume acceleration is constant, just like we assumed velocity was constant in the previous equation. The force that we want to model is gravity, as we just seen before. In this equation, note that v actually represents the change of position with respect to time. So it's like a differential equation inside a differential equation. It's like equationception. Together, these are the full sets of equations that my space simulator solves, and we solve them in a manner very similar to the way that we actually solved our first example. Okay guys, let's get on to the fun part, demonstrating the finished product that I briefly showed you earlier. Hello? Guys? Hello? Okay, time to wake up now, nap time's over, this part's actually fun. So here we have our finished spaceflight simulator program. In this left monitor here, you can see the Earth, the spaceship, and the white line that represents the spaceship's trajectory. In this right monitor here, you can see the view from the spaceship. Right now, the spaceship is in a circular orbit. In fact, you can even see the Earth going by in this right monitor here. Unfortunately though, this is real time, and in real time, things take quite a while, and I don't really want to sit here waiting while this spaceship goes all the way around for a day. So I implemented a time warp where I can speed up and slow down time. And now that I've sped up time, you can see that the spaceship does indeed follow the trajectory that's been plotted out for it, and it does indeed travel in a circular orbit. Something interesting to note is that if I apply thrust in the direction of travel, my orbit goes elliptical. I'm just going to zoom out a bit so you can see that. You may notice that the trajectory is a fixed amount of time, and it doesn't right now encompass the whole orbit, so I'm just going to extend the trajectory so you can see the full elliptical orbit. Something interesting to note about elliptical orbits is that the farther away you are from the Earth, the slower you go. And the closer you are to the Earth, the faster you go. So that's because as you get closer to the Earth, gravity gets larger, and therefore you travel at a higher velocity. Another interesting thing to note is that if you actually apply too much thrust, you actually can leave the Earth's gravitational field and achieve something called escape velocity. So as you can see here, if I apply too much thrust, my trajectory goes way out, and if you advance time, we can see that the spaceship just goes on, and eventually escapes the Earth's gravitational field, never to come back. Keep in mind that all of these trajectories are being created by numerical integration. However, I've actually done the math for these, and these trajectories calculated by numerical integration are indistinguishable from the exact analytical solutions, which is very impressive if you think about it. So, again, although circles and ellipses do have analytical solutions, there is a scenario in which there is no analytical solution, where numerical integration becomes very handy. Right now, the Earth is being affected by two celestial bodies, the Earth and the Moon. And for this scenario, no analytic solution actually exists. As you can see, this trajectory here doesn't satisfy any mathematical equation. So, as we've seen before, analytic solutions exist for one other celestial body. So, if we were going to try to use analytic solutions, it'd be pretty reasonable to use the Earth because its gravitational pull is bigger than the Moon's. But if we only account for the Earth's pull when we do our analytical solution, we get a perfect circular orbit, which is very different from what actually happens, as you can see here. And you know, if we're launching a rocket to the Moon, for example, we don't want to go, "Oops, sorry Armstrong, forgot the second celestial body. Didn't think you'd run out of fuel," but don't worry, don't panic, we fixed the program bug. We want to know what's actually going to happen, and for that we need to use numerical integration. So what's actually happening is, even though the Moon's gravity is small at first, the Moon pulls the spaceship closer and closer to it, which makes gravity bigger and bigger, until eventually the spaceship is slung around. Ooh, pretty textures. Man, this game is really fun, and it's all possible because of numerical integration. Okay, I think that's all I have for you guys. Thanks for watching. Patrick Ko, signing off.